Hello everyone, welcome back to the episode 12 of the number series. And for today's video, we will be talking about the exercises at the end of the section 12. Let's begin. So question number 1, adapt the method used in the text to evaluate 2 slash p to evaluate the 3 slash p. So first, we're gonna test how many numbers are within those two ranges, because those two ranges is going to have the number that has remainder less than or equals to the p minus 1 over 2, and then we're gonna subtract that from the total total of how many numbers are there, and those are the result of how many numbers are within those ranges, and according to their if they are odd or even, they will be either have a solution or have no solution. And question 2, show that 3 is a quadratic non-residual of all primes of form of 4 to the power of n plus 1. So we use the quadratic reciprocity, we flip it, and it's going to be 1 to the power of n plus 1 slash n, no, slash 3. So 2 slash 3, according to the theorem 6 from the last chapter, we know that if 2 slash a number that has a remainder of 3 or 5, it has no solution. Sorry. Question 3. Show that 3 is a quadratic non-residual for all the same prime greater than 3. Again, very similarly, we know that this is in a form of 4k plus 3, and we have a negative 1 when we flip it. And we take the remainder of this one, we get negative 1, and since this is odd, we get this negative 1 here, and we go negative 2. We factor out the negative 1, and we figure out the result as negative 1, which means it has no solution. Question 4, prove that if p is congruent to 7 modulo 8, then p is the divisor of 2 to the power of p minus 1 divided by 2 minus 1. This is basically equivalent to prove 2 slash p equals to 1, because according to the Euler quotation, this thing is congruent to this expression, and since this is p is congruent to 7 modulo 8, it is congruent to 1. Okay, part B, part B, yes. Find the factor of 2 to the power of 83 minus 1. We know that according to our conclusion in A, then 167 should be a factor because this is a prime and it has some very similar form like this. Question number 5, if P and Q equals to 10P plus 3 are odd primes, show that P slash Q equals to 3 slash P. So using that P is odd, we can determine the remainder of Q of modulo 4, and we find it is equals to 1, and then we can just flip it. So P slash Q equals to Q slash P, and we sub in the expression for Q, and we get this, and we take the remainder, it's equals to 3 slash P. And part B, we need to prove that if p and q equals to 10p plus 1 are odd primes, show that p slash q equals to negative 1 slash p. So we can discuss two different cases where if p is congruent to 1 modulo 4, and we find that it is equals to negative 1 slash p when we flip it and then take the remainder. Well, if it is congruent to 3 modulo 4, it is still equals to a negative 1 slash p. Therefore, it's true. Question 6. So which prime can divide n squared plus 1 for some n? So this is what the question are asking for some number n, and when does this when is this true? This is asking when is negative 1 a quadratic residual, and we know that this thing have a solution exactly when p is congruent to 1 modulo 4. And part B, which odd prime can divide n squared plus n for some kind of n? This is what the question are asking, and we use the technique to complete the square, and we have this to be the remainder. Since this is already a square, then it is always going to be 1, and therefore all kinds of p have some kind of solution. So question part 3, for which odd prime can divide n squared plus 2n plus 2 for some kind of n? Well, this is what the question is asking, and we still need to find negative 1 to be a, when does negative 1 become a quadratic residual of modulo p? We know that if p is congruent to 1 modulo 4, it has solution. If question 7 show that if p is congruent to 3 modulo 4, then a is a quadratic residual modulo p, then p minus a is a quadratic non-residual. So we know this is true, and we gonna take the remainder and factor out the negative 1, and we know this is equal to 1. That means it must be equal to this. And since p is congruent to 3 modulo 4, then it's a quadratic non-residual. If this thing is congruent to 1, then it is a quadratic residual. Question 8. This is one of the most interesting questions, I think. So if p is greater than 3, show that p divides the sum of all of the quadratic residuals that are also the least residual. So the sum of the quadratic least residual are given by the residual of those numbers, and each number will provide a unique residual, because if they are congruent to each other, then it means this thing shares some kind of factor of p. But we know that the range tells that this is impossible, therefore each residual is unique. And the sum of this expression equals to this, and we can show that this thing is also always an integer by using a list of table. Therefore, it is always a multiple of p. And so the sum of the residual is congruent to this sum over here, and always multiple of p. And question 9, I couldn't figure out what is going on. It's just that the answer is always negative 1, and I don't know how to prove it, sorry. And question 10. So, question 10 shows that if p is congruent to 1 modulo 4, then x squared congruent to negative 1 has a solution given by the least residual modulo p of p minus 1 divided by 2 factorial squared. So this thing, we can rewrite it. First we expand, and since there are an even number of terms, we can just put a negative sign at the front for one of the p minus 1 over 2 factorial, and then we're gonna, for those negative, we plus p, since we are talking about the congruence, and we get exactly p minus 1 factorial. According to the Wilson series, it is congruent to negative 1. And that's the last question for the today, because this is a very short chapter, and I'm a little sick, sorry, and see you in the next video. Goodbye.